We're going to start this second part of the Maxima matrix menu, talking about eigenvectors using the same document that we used before. Now, remember the matrix D was a symmetric matrix, and so I'm going to use the command eigenvectors. Now, this is even more complicated and quite elaborated result. Now, there's not much you can do with that. It's a complex number, a very complex number format. So as we did with eigenvalues, we're going to do eigenvectors float numeric to rectangular form. To simplify them and simplify that result, we get something that's a little bit more readable. But you still have a lot of negligible imaginary parts. That one right here, another one right here, many others. So we want to get rid of all those negligible imaginary parts by using real part of the last result, and we're going to store that into a list called L2. So we have used L1 for the eigenvalues. It turns out that there are two lists within that list L2. One that begins right here and ends right here, and one that starts here and ends right here. The first one is just the eigenvalues with the multiplicities. So if I extract L2 1, I get the eigenvalues, and then I'm going to ignore that part because I already have those. L2 will give me eigenvectors. Now there is like two levels of brackets in here. The most interior one is actually a vector like a matrix with one row and 3 columns. And so I actually, in order to extract these elements, I need to have two extra subindices, 2, 1, 1, 2, 2, 1, and 2, 3, 1, because in every one of them there's only one element, but they are 1, 2, and 3. And so I store, this is x1, x2, x3, the vectors. Those are my eigenvectors for this problem. It turns out that if the matrix is symmetric and the eigenvalues are real, the eigenvectors must be perpendicular to each other. So the dot product of two of those eigenvectors must be equal to 0. The dot product is calculated in Maxima using the command inner product. And then what I did, I converted this to float because the way that it is presented is in a symbolic manner, like a fraction. And that actually is a very small value. Same here and same here. So they're not exactly equal to 0 because of numerical error, but for all practical purposes, those cross products are indeed 0. Then we go back here and we're going to do matrix determinant. I actually skipped it somehow. And that just inserts the command determinant, and you know how to calculate the determinants for given matrices. I think I have a matrix K, which is a 2 by 2 matrix. If you do determinant K, you get A times D minus B times C. The adjoint matrix has to do with the transpose of the cofactor matrix. You can read about the cofactor matrix in this link. And the command that results is called adjunct, and I give you that matrix. The rank of a matrix is determined by using the command rank. And then again, all of those are available right there. Got ranks for matrices C, D, and E. All those are regular 3 by 3 matrices, and there's no problem with them, so they all have rank 3. The transpose, again, available right here as transpose matrix, is when you exchange rows with columns. And so, for example, for matrix A, you have A11, A21, A31. Now you have A11, A21, A31 with this column. This row became this column, this row becomes this column, this row becomes this column. Transpose of C give you the same result, 5, 6, 2, minus 5, plus 6, minus 5, minus 2, 8, 4, minus 2, 8. So, extract row, go to matrix, extract row, extract matrix row for matrix B, row number 2, for example, results in this command, and it extracts a vector corresponding to that row. Extract column, when you activate this, you get something that says extract a matrix row. That's a typo, it's a mistake. But actually the result is correct. It gives you column. And it will extract the second column. Rows or columns is actually we extract a submatrix. And so it says, for example, matrix A, rows 1 and columns 2. You see there, actually took out rows number 1 and column number 2. Convert a row to list. We have the for matrix C, the second row, converted to a list. You can use the form, of course, that comes out. Convert a column to a list. Again, it refers to matrix row. That's wrong. It should be column, but the result is correct. Matrix multiplications. There's a form for it, but it turns out that to multiply matrices in a matricial way, you have to use a dot. If you type A times C, you get your matrix multiplication. C times D, you get your matrix multiplication. Matrix exponent uses 2 carets. Now, if you want to multiply element by element, which is called the Hadamard product, you can activate the form using Hadamard, or simply use the regular times. C times D, C